Okay, we're going to get started, but I'm excited to welcome everyone to the inaugural SIAM Industrial Lightning Symposium. It's organized by the SIAM Industry Committee, and Nessy, Tania from Pfizer and the Industry Committee was the lead on that. I'm Sharon Arroyo. I'm a Senior Technical Fellow at Boeing, and I'm the VP for Industry. So it's with great pleasure to introduce our two inaugural Lightning Symposium presenters today. The first is Dr. Gwen Spencer. She is currently a senior machine learning scientist supporting the content and finance orgs at Netflix. Dr. Spencer transitioned to industry 5 years ago after several years teaching at Smith College. Introduced to mathematics by a parent volunteer who coached her local high school math team, Gwen is a graduate of Harvey Mudd's College Math Department and Cornell University's School of Operations Research and Industrial Engineering. Her talk will be titled, Take Delight in Cold Showers. And then Dr. Wotao is currently a research scientist, principal engineer, and the director of the Decisions Intelligence Lab at Damu Academy of Alibaba Group in the US. He obtained his PhD in operations research in Columbia. Prior to that, he was a professor in the Department of Mathematics at UCLA. Dr. Yin's research has been recognized through external awards and citations. His research interests include decision models, computational optimization, algorithms, and applications in signal processing, machine learning, and other data science problems. His title is Beyond Technical Proficiency, Essential Skills for Success in Industrial Research Labs. So thank you and welcome, Gwen.
Great, well, thank you so much. The motivating question that I was thinking about in creating this talk was about what the core contributions are that a mathematician can make in industry. And I think, you know, the obvious answer is that we bring this math part, right? Industry wants it, we can bring it. But actually, the math part doesn't get up on Monday morning and go to work. So I really want to talk about this whole package, the mathematician or the person who practices mathematics and the contributions that they can make. In my experience, the contributions that you can make has a lot to do with the kind of professional skills you invest in. So I'd like to tell you today about some investments that I've made that I've found really rewarding and even, in fact, delightful. So in my career in industry so far, I have an almost one-to-one ratio between the number of years I've spent and the number of problem spaces I've gotten to work in. And in particular, I started in the logistics industry where I used spatial optimization to design Convoy's coordinated marketplace of trucking jobs that are offered for bidding to tens of thousands of small independent trucking companies. Then I moved to a company called Stripe in the payment processing industry and used forecasting and queuing theory to deliver exceptionally responsive customer service to the millions of businesses that process in total over $1 trillion a year on Stripe's internet payment infrastructure. Then I moved over to support the treasury group at Stripe, where I was using large-scale simulation and extreme scenario modeling to size and rebalance liquidity buffers that Stripe holds across its network of international entities in a number of different currencies, so that in cases where cash outflows briefly exceed cash inflows, the payment of customers is never interrupted. And finally, I now work in the entertainment industry where I use machine learning and optimization to reason about how to increase subscriber value as Netflix strives to entertain and thrill our vast and diverse international member base. If this seems like a lot to do in 5 years, like, yes, it is. This is a whirlwind tour. If you're a fan of multi-armed bandits, you could say I've been in explore mode. And in this time, I've been accruing a lot of observations about how to do effective work as a mathematician in industry. Some of those vary across dimensions, like the stage that the organization is in. How you do effective work in an early stage startup is pretty different from how you do effective work in a mature 20-year-old company. But there are some ways of doing work and delights of doing that work that I think really translate across a lot of the common dimensions of industrial positions. And I'd like to tell you about 3 of those today, starting with the delight of deep partnership. So I didn't get a PhD that was in any way really related explicitly to logistics or fintech or entertainment. I knew very little about these fields when I entered these companies. But I had the privilege to learn about the concerns of these domains from really talented and generous partners. Okay, some vocab from industry that I use interchangeably are my business partners, my stakeholders, my domain experts. And the reason that I value this partnership so highly is because my core ability to contribute as a mathematician in industry is critically dependent on solving the right problem, really being focused on the decisions the business is able to make and knowing the space of feasible actions that the business has, being able to discern between what's a hard constraint and what's sort of a soft, nice to have. And also, partners are highly aware of the quality of different inputs and observations we have about the past that potentially serve as the foundations for models that I'll build. So if I don't know where to be skeptical or where to be careful and where I can confidently depend on the quality of the inputs that we have, it's going to really compromise the work that I can do as a mathematician. I'd like to give you an example from my time in logistics where we had domain experts in the loop, and it dramatically changed what we were able to accomplish in the course of the project. So this is a spatial rebalancing problem. The spatial scale is North America, and Convoy's business plan is basically to take thousands of jobs that are being executed for hundreds of different shippers and aggregate those and offer them in a marketplace for bids by independent trucking companies. So there's sort of tens of thousands of small independent trucking companies that are coming to this marketplace looking for work. And Convoy is agreeing to shippers that they're going to do sort of a certain volume of work, but the job details arrive online. And then once those jobs are actually contracted, they create a flow across North America of Convoy's trailers, that is an asset of the company, that can, if left to sort of flow organically, result in large buildups in some region of the country and large deficits in other regions of the country. So Convoy was a startup. It's actually no longer in business. That happens with startups sometimes. But this is a highly similar spatial rebalancing problem to that faced by many shipping companies, rental car companies, ride-share companies when you look at more of a city scale, spatial scale. So our algorithmic goal in this project was to frequently replan the shape of the jobs that we were offering in the marketplace to keep Convoy's trailers balanced and well staged to perform the subsequent days and weeks of work, while also minimizing the amount we were transporting empty trailers. That costs money, and also from a sustainability perspective is just like not great to be accruing those empty miles. So after an initial round of modeling, I introduced the Trailer Rebalancing Integer program, which we named TRIP. And we started a series of daily morning meetings with our domain experts who are manually managing the system. Our engineering partners were key here because they built a UI so that our partners could look at an explicit list of the recommendations from the automated system and opt in for the recommendations that they liked to flow those directly through to the marketplace within a minute. And we had some quick wins because so many of the recommendations from the automated system, our domain partners really felt were common sense recommendations. They would come in and they would say, I knew I was going to have to change some of these jobs out of Indianapolis today. You just saved me a bunch of time, and they would flow those through. But at the beginning, the automated system was also making some really embarrassing mistakes. And the reason here is one that comes up a lot, which is that the automated system that only knew what we had told it about. So in particular, we found over time, by looking at the flavor of mistakes it was making, that we were actually constraints that we hadn't captured about the system, things we hadn't known to ask about, and our domain partners hadn't known to tell us about how the system should behave. And we were able to discover those constraints through the process of showing them these proposed solutions. There were also places where we had encoded something that they had told us about as a hard constraint, and then they came and said, oh no, you shouldn't spend this much money to do this kind of a thing. And we said, wait a second, you told us this is what it means to be feasible. And they said, yeah, but don't spend $2,000 to do that. Okay, so there were places where what we needed was actually a soft constraint rather than a hard constraint. And we discovered that by working hand in hand in these day-over-day meetings. And we also had to navigate some pretty surprising discrepancies between the ML predictions about the costs associated with certain jobs and the mileage associated with the length of those jobs, and decipher whether that was a real signal about the value associated with doing that work for different trucking companies. So there's certain cities that truckers love to end up in because they know they can get work outbound from those cities. So if a job goes into that city, the price of doing that job that goes into that city is going to be quite favorable. So our business partners were extremely pleased when they saw the automated system behaving better day over day as we told it more about what it needed to do. And our small team of 3 to 4 domain experts, 2 scientists, and 2 engineers were able to squash many, many flavors of misunderstanding and push up that percentage of daily changes that were being accepted by the human experts from 85% to 90%, 92%, 95%. We were getting so close. And actually, it turned out there was something really cool happening among the stragglers. My business partner actually spotted this before I did. I should have suspected it. As a fan and booster of optimization, I should have had high expectations. But what my business partner noticed is that what was left were small, coordinated subsets of changes where the algorithm found opportunities to make things slightly worse for job A, job B, job C, so that it could make something much better for job D. And it was really cool to realize that this got us basically to 100% accepted changes from the suggestions of the automated systems. So we turned that on, and the takeaway I'd like you to take from this anecdote is that the difference between an interesting initial idea and implementation in a deployed system that's actually coordinating the movement of thousands of huge objects is deep partnership. It makes it possible, and it makes it possible really fast. We went from basically a toy model, toy implementation, to a deployed system in about 3 months. So the next delight I'd like to talk about is the delight of building traction about real complex systems. I've said a lot about the level of domain knowledge that partners have. What does a mathematician bring to the table? So I've personally gravitated towards earlier stage companies or newer problem spaces at large stage companies. And there, a lot of what a mathematician has to offer is about generating a formal language to talk about a highly ambiguous problem and being able to quickly explore what the implications are of that formal language and what consequences follow from a particular set of assumptions about how the system works. And then being able to lean on formalism in a way that can extend an initial understanding of the system that's maybe shared by partners who are less technical in order to get to a place where you have actionable suggestions. When you put shape on an ambiguous problem, mathematicians are very, very good at understanding to what degree that shape aligns or departs from known results. If the wheel works, just use it, okay? One of the ways in which things can be more complicated can be that there exists a methodology for a particular area, but the assumptions that are typically used for the big message sort of takeaways in that area don't quite hold about your real system. So there, a mathematician can also work to peer around the corner and understand whether sort of the findings of that methodology are going to be still fundamentally true or going to be really eroded by that assumption not quite holding. Here's an example from tax season in my time in the payment processing industry. So a year is a really long time in a hyper-growth company. During a year, between tax seasons, your customer base changes, the product you offer changes substantially. So the first part of our goal was a forecasting goal where we have to produce at 15-minute intervals an inbound contact volume forecast for a number of different channels. And we had to layer in a lot of step functions that had happened since the previous year that we basically couldn't address with standard time series methods. And then we had to take that forecast, which we already knew had a lot more uncertainty than our typical forecast, and we had to think about how to plan with it. So this is a very standard queuing idea, right? Given some response time target, go ahead and come up with an estimate of the number of support agents you're going to need to staff at each time of day in each contact channel. A key point here, if you haven't thought about this area before, it gets really easy if you don't mind spending a lot of money. So if you just go ahead and spend 10x more than you think you have to, okay, now you can very confidently meet whatever service targets you specified. But of course, that's cost that you would have to pass on to the customer. So as I was working with my partner, we talked about our existing planning pipeline that was working really well during normal weeks, but we knew that as we went into tax season, we had tuned our planning buffers really, really lean because we had been working with a forecast that was performing really well, that had really high prediction accuracy. And we also knew that we had seen within day arrival distributions in the previous tax period that were very different than our normal weeks. Okay, so we started to talk about how are we going to need to plan differently than during a typical week or month. And to do that, to reason about that, we estimated how much the backlogs could blow up if we applied sort of a typical planning pipeline. And we talked through scenarios both where the forecasts were actually underestimates and also where the forecasts were actually right at the daily level, but underestimated those peak arrival rates. This forced us to get precise about recourse actions in a way that, you know, as someone who studied this topic in a stochastic processes class in graduate school, I had never really occurred to me, like the idea that you could pulse, for example, your service rate in a queue. So we had to get precise about recourse actions and reach out to vendors to understand how many overtime shifts they were going to be able to reliably deliver in different time zones. And we talked through, you know, okay, if queues blow up at these certain peak times of day, how much capacity can we add to sort of outpace arrivals? How long is that going to last? Is it going to be enough to bring down the backlogs? We were able to use our complementary knowledge to think through the hazards and recourse options. And this really enriched my appreciation for stochastic processes. When I learned it in graduate school, I thought it was an elegant topic. I loved going to those lectures. But when I saw that this was an actual set of tools that could be used to control such a messy real-world system, this was like quite profound to me as a professional. There's also a lot of building traction about real complex systems that happens in larger companies and more mature problem spaces. In the interest of time, I'm going to go ahead and skip forward a little bit here to what I've promised you about the delight of a cold shower. So this is actually also an anecdote about tax season, but kind of in a more general sense. So what is tax season in the fintech industry, if not sort of a huge tidal wave on the horizon, a demand surge? Okay, what is a global pandemic in the logistics industry, if not a huge tidal wave on the horizon? Even viral popularity and entertainment lifts some small boats to incredible, astounding heights and swamps other big projects that were considered sure to succeed. So when I talk about cold showers, I'm talking about the onset of a highly taxing event that often carries substantial uncertainty. In this setting, automated systems are going to really struggle to perform well. And I think that one of the delights of practicing mathematics in industry is getting to see your best ideas about how to manage a system and how to control it really straining and really struggling to perform against the real world. Sometimes you get good news, right? And other times you get a very, very cold shower. And I think as long as you understand these cold showers as an invitation to iterate, you can really derive a lot of delight from them. Because if you take them as an invitation to iterate, you can understand what fell short about your V0s. You can investigate and then start to grapple with this unbelievably wily space of instances compared to what you thought you were doing battle with. And you can decide to deprecate those favorite first ideas in favor of later versions with better capture of the system. This allows you to practice some of the most essential habits, I think, for contributing in industry, in terms of being able to regroup and reflect, to up-level sensitivity analysis, to design for better robustness, and ultimately build a stronger approach. For those of you who are already working in industry, I hope some of these observations from Explore Mode have resonated with you about your own experience. And for those of you who are either students or faculty who advise students who are considering careers in industry, I hope I've managed to share some of my enthusiasm and true sense of engagement that I've experienced in just a short period on this career path in industry. So thank you so much for the time.
So hello everyone, I'm Wotao, and I began my career in academia. I spent about post-PhD 13 years in academia, and then where I did lots of algorithms and math. I built up on that with some good results and reputation in large-scale optimization. and machine learning, which helped me land in a leadership position in an industrial research lab, where about 20% is to serve internal customers and 80% is to serve external customers. So it's very challenging. These days, there are more positions in industry than in academia, so I know many students and some faculty members also considering transitioning from academia to industry. So I consider my audience as these people. So I want to share my experience of this transitioning, highlighting some of the critical differences between academia and the industry, and the valuable lessons I have learned. The obvious difference is how you get an interview. Well, to secure a job interview, you present a CV in academia, which lists your publications, teaching experiences and awards, and maybe funding. It's about the contributions you've made in research and education. But to get a job in industry, you present a resume. The resume usually do not have the full list of publications. Instead, you list your roles, the roles you did, the skills you have, and the project experience. Because it's not about what you have done in the past, it's more about what can you directly contribute to the company. So it summarizes innovations for the product and services that can get paying customers. The next difference I want to talk about is the collaboration. Both industry and academia value collaborations, but the form differs so much. In academia, we team up with other researchers, sometimes also engineers. But in industry, the team can be really have very diverse members. Usually, there's a project manager, can also be a product manager, and there are scientists, researchers in the team. We often also have engineers of different kinds who, for example, develop a infrastructure, who are in charge of something called continuous integration, continuous development, or testing. If you are building a real product, then you also have product manager, designers, and if you have passed the initial phase, you go into production phase, you're also talking to marketing and sales personnel. And also the way they collaborate is a little different. Although we do present in conferences like SIAM, the essential communication tool is writing in academia. So we write reports, articles, and papers. But in industry, we have more meetings face-to-face or on Zoom, which means you have to use a language that's really efficient at delivering your core messages. For example, we have to avoid lots of scientific jargons, because if you speak that, not even all the scientists on the team will understand what you're talking about. So instead, we use sales. If you can speak sales language, everybody can understand. Another difference I want to mention is the project, the scope of the project. At universities, if we have an idea, and we usually go on with proving some theorems, showing the values of the idea, and doing some experiments. And then we write up everything in the paper and submit the paper. Once the paper is accepted, our job is pretty done, unless you want to promote your work. But in an industrial project, it's a much longer horizon. It's not just about initial ideas and concepts. You have to prove it's valuable to final customers. So there's a phase called POC, or proof of concept. And then there's a phase, if you pass the POC phase, you're into the phase called the minimal viable product phase, which is essentially the simplest version of your product or your service that can deliver the core value, do the main job, and there are going to be people started using the product or service. If you're lucky, you pass the MVP phase, then you're into a more serious production and service phase. I call that phase 1 to N. Now, if you look at whole horizon, there are two issues that cause the differences between the two. The first issue is the scalability and the cost. If you do an internet scale algorithm, it's not going to be just a few variables. It's millions or even billions of variables. So your simple algorithm needs to also work in big scale. And the cost is not just the cost of these people and these time. It's also the cost of maintenance. Is your algorithm robust? Do I have to regularly revisit the parameter of the algorithm? Or do I have to go back to the customer, retrain the model every 6 months or so? Those are all costs. Another difference is the time scale. A typical university project lasts about a few months, maybe go up to a few years at most. But every project in the company will usually have weekly meetings, maybe bi-weekly meetings. And the team will be seriously reviewed every quarter or every 6 months or so. So these frequent reports and feedbacks will help you keep on track. But there's also an issue with reporting, because often you're not reporting to the people that have the same technical backgrounds. So independent contributors, ICs, have reports to managers, and managers have reports to, let's say, VPs, and VP reports to CTOs or CEOs. And very unlikely you will have people who come out of the same profession, the same field in school with you. So you have to speak simple and concise language to make the communication effective. So I hope these differences are going to help you understand what the transition is like. And now let's talk about an essential skill, I think, that the academia didn't really talk about, which I call strategic thinking. Well, the background of strategic thinking is industry R&Ds, research labs, is subject to both time and other resource constraints, and we're also facing competitions. You think you have a great idea, there might be 2 other labs in the same company or in different companies doing the same. You have to win. So strategic thinking becomes vital. Strategic thinking is not about a goal. Let's say you say, I want to write a great paper. That's a goal. It's not a strategy. Let's say you have an idea of a great product and you divide it into steps and milestones. That's called a plan. It's not a strategy. So strategy is a rational thought process about the bigger context, the critical factors, the variables, and you have to come up with decisions, informed decisions that lead you to success. So as I mentioned, we hardly ever talk about strategic thinking in academia, but I think we can practice it at school. Let me give you some examples. Suppose you are looking for a research topic. The common practice is I follow my interest and I base that on where there's a gap or maybe gaps in the literature, and I work on that. That'll give me a great paper. But that's not enough. Strategic thinking means you also think about emerging trends and think about maybe a pathway of multiple projects that will eventually lead to a coherent body of work. Well, because if you think it that way, you may have luck, maybe a better chance at fundings, and you may get yourself become a leader in an area. And let's say you have chosen a research topic and now you want to build a team. Building a team, the common practice is to just find the people we are familiar with, we have worked with, and who also share the same interests, and let's work together. That's also not enough, because if you think about, let's say, a treasure hunt game, you're going to need people who are going to read maps or mapping very fast. You want to also have people who are strong, who are good at digging, and you also want people who are fast because they can explore. You need to have people of different skills who can bring fresh perspectives and who can maybe apply your methods to new applications you never thought about. Even though it means you're going to take time and energy to meet new people and get trust between you and them. So in conclusion, transitioning from academia is not just about technical proficiency or getting good at coding for students. It's more than that. Strategic thinking, effective communication, team building, risk management are all essential skills for industrial success. And thank you for your attention. And I hope these insights can help you understand industrial research a little better and help you navigate your potential transition.